I'd like now to introduce Keith Devlin. Keith is a mathematician, director of Stanford University's H-Star Institute, and he's also a co-founder of BrainQuake, an education technology company that builds mobile games for mathematics learning and assessment. He's a fellow of AAAS and fellow of the American Mathematical Society. His current research focuses on the use of different media to teach and communicate mathematics to diverse audiences. He has also worked on intelligence analysis projects for the US Department of Defense. He has written 33 books, not a typo, and 85 published research articles. He's the math guy on National Public Radio in the USA.
A couple of words about my background, which I need the microphone. A couple of words about my background, which may explain where I'm coming from. I spent the first 20 years of my career in pure mathematics, not just pure mathematics, but mathematical logic, where we use the tools where we distinguish between syntax and semantics in order to answer questions in mathematics. So the first 20 years of my career doing pure mathematics, looking at how mathematics was represented in different representational systems. Then in the 1980s or thereabouts, I switched and ended the rest of my career working very much applied in work, doing consulting work or research projects for industry. And then after I moved to the United States, even more so, consulting for various parts of the Defense Department. So I've got this background in pure that changed to the last 20 years almost now, more than 20 years I guess, of working in very applied disciplines on real world problems with many variables and a lot of complication. Okay, key observation I want to start with. For several thousand years, calculation was the price we had to pay to learn and do mathematics. If you couldn't calculate, you couldn't even get into the club. And once you were in the club, you had to calculate every day to go on making progress. You had to do your own calculations because there was no other way of doing it. Human beings were the computers. The key word here is had. Because about 1987 is the date I would put on it, is when that changed. Because it's no longer the case. In 1980s, I picked that date because that was when Mathematica was first released. I'm not using Wolfram as an example because Conrad Wolfram is speaking later. It's just a system that I used shortly after it came out, there were other systems. But from the late 80s onwards, human beings have not had to do calculation of any kind, not just numerical, but algebraic, geometric, any calculation, any procedure, any algorithmic process. We have no longer had to do it because machines could do it for us more accurately, faster, with many more variables. You probably all recognize this. One of the most famous buildings in the world, the cathedral in Florence. It took 140 years to build that. You probably recognize this building, Sydney Opera House. That took 14 years to build. Boy, is that a difference in time. These are big buildings with lots of architectural challenges, lots of construction challenges over different periods. One took 140 years, the other one took just 14. Why did the first one take so much longer, 10 times longer than the second one? Well, obviously something changed in the Interbarian period with the way buildings were designed and put together. What changed? Well, it certainly wasn't about architecture. This is both good architecture. It's all about having good aesthetics. It has sound construction techniques. You still have to satisfy the laws of physics. None of that changed. The basic principles remained the same. What changed were the tools that were available. In that intervening period, a lot of tools came on the market and became available for people to design and construct buildings. Which means that today's architects, the designers and the builders, equipped with a different tool set, need a very, very different basic skill set in order to do their work. The basic idea is the same issues are important, but different tools mean the practitioners need to have different skill sets. Well, we now have quite an array of tools. We have an array of tools available to us doing mathematics. This is my list. It's in order of importance, reading left to right. In all of those years working for industry and the government in different branches, The tool I used first of all, whenever I was in a new problem, was Google. The second tool was almost always Wikipedia. Then I used email. Then I used, when it became available, I used Wolfram Alpha. Then I almost inevitably go to YouTube because I need to learn some new techniques, and there's almost anything you want to learn about, there's good YouTube videos. At some point I'll probably bring in a spreadsheet to look at some actual data just to get a sense of the size of the problem. Then I might use something, I actually don't use MathLog myself, but a lot of people do, so I put this one in. Because I have a good network of professionals, I use LinkedIn. I sometimes at some point contact people that I think might help me. There's a mathematician's equivalent of the computer scientist, the computer developer Stack Overflow called Math Overflow, where you can put nerdy, detailed technical questions and get them answered, often within a few minutes. Then there's Wolfram Mathematica, the basic computer algebra system that came out in the late 80s. I sometimes, very occasionally, will go on Quora, which is a sort of a nerdy question and answer thing where you can do sort of short essays, long answers. Because I have a reasonably large Twitter follower, I sometimes use Twitter. I actually don't use a calculator, but having given this talk several times and put this slide up, many people say, what about the calculator? Well, okay, I'll put it there because it is a valuable tool that many people use. I don't use it simply because those other tools have much more power available to me to use anyway, so I've already used those. There is one more tool. It's that guy. That hasn't gone away. I don't think I've ever solved a problem when I need to sit down and write something down. But basically, until I get to here, everything I'm doing is avoiding reinventing the wheel. I'm not going to waste my time and my intellect reinventing the wheel, doing something that's already been done. If it's an important problem, someone has probably thought about it or something similar. And most times I can get 3/4 of the way to the solution with known tools and looking things up. Then I'll have to do something different. If I don't have to do something different, I wasn't really necessary in the first place. Somebody else had done it. You just write a report and leave. But the ones that are interesting, the ones where I'm actually needed, I always have to use that as well. But that's my tool set. Different mathematicians. By the way, I posted this on a blog earlier this year, and quite a lot of professionals in mathematics and engineering basically wrote in and said, yeah, that's more or less the same as my toolkit as well. This isn't just me. This is how the pros do it. These are the tools we use and have been using since the late 80s, early 1990s. So that's the tool set. So the question might be now, does that mean we no longer need to teach calculation? No. What a stupid thing to suggest. The only people that suggest that have a political agenda, which means they're probably trying to sell textbooks or calculating devices or something. Of course not. What's different is we no longer need to teach for fast execution. In fact, today's problems that we need mathematicians have so many variables and so much complexity that there's no way you could do it in your head. You'd need the technology anyway. What you need to be able to do is understand how to use those technologies. So we no longer need to teach for execution because that's not done anymore. The machines are faster, more accurate, totally accurate essentially, and they'll deal with 100 variables, 1,000 variables, 1,000,000 variables. It doesn't matter. Human beings can handle 2 variables, 3 variables, and if we're prepared to tolerate the risk of making mistakes, 4 variables, and that's about the limit of it. What we need to be doing today is teach the stuff for understanding, which means just like the architects and the builders building the Sydney Opera House, today's professional mathematicians use a very different set of skills in order to do mathematics. In fact, in January of last year, I wrote an article on the Huffington Post that got absolutely viral. I mean, this got thousands of hits and not tens of thousands, hundreds of thousands. It was one of the most read articles on Huffington Post at the time. And the title was, "All the mathematical methods I learned in my university math degree became obsolete in my lifetime." Obsolete in the sense that human beings no longer do that. They simply don't. They use the tools for the reasons I've already mentioned. So, what now? In a world where that need to learn calculation and procedures is gone, what do we need to do? So what and how do we teach for life in such a world? Well, we really need to go back and reassess what this whole thing's about. Why mathematics is developed, how it's developed, and how it's used in the world. And I am talking about mathematics in the world. Pure mathematics done for the kind of reasons I did it for the first 20, 25 years of my career, that's not going to go away. That's still done in essentially the same way as it always was, with some differences, because even the professional pure mathematicians use technologies when they can. Okay, well, here's typically how mathematics has been used throughout history. You begin with some real-world situation. Imagine you're going to build a house. You have ideas, you talk about it with your family, you have ideas about what you want it to look like, what it should feel like, how you're going to live in it. You talk to an architect who translates your needs, your desires, your goals, into the language of architecture, affordances, adjacencies, etc., 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 aspect ratios, light plans, and so forth. It's now written in a technical language of architecture. The architect then brings in a draftsperson who turns it into blueprints, spreadsheets, all of the mathematical descriptions, the geometry, the trigonometry, that comes in. You're now into the language of mathematics. Once you're in the language of mathematics, you can do all the calculations, how much material is required, what it's going to cost, what the production schedule is going to be, how long it's going to take, yada, yada, yada. You can hire people, do the mathematics, you get the mathematical results, and then you feed it back into the world, and people arrive on the land and start building the house. And during the course of construction, you probably cycle through this thing several times as you make discoveries on the way. That is the way mathematics has always historically been used to meet a need of society, and we follow it through that way. This part on the right is typically called a mathematical model. A classical example would be geometry. Some mathematical models are so useful and so universal that they become classified as models, not just of models, but as branches of mathematics. So these become the established models. So geometry, which was originally developed for sort of measuring the land. When you add angles and things, you've got trigonometry, where you can use it for navigation. But it's a model of the world. The world doesn't actually look like that, but it's a useful way to think about the world. Okay. How does this work in practice? Let's just spell it out. This is what happens. When you're applying this thing called a mathematical model, the mathematical method, you identify a particular pattern in the world, you study it, you develop a notation to describe it. You use that notation to further the study. You formulate basic assumptions, what we call axioms, to capture the fundamental properties of that pattern. You study the abstracted pattern, establishing truth by means of rigorous proofs from the axioms. You develop procedures that you and others may use to apply the results of the study to the world, and then you apply the study to the results to the world. So that's typically how it's taken place, going back to Aristotle, the Egyptians, the Babylonians, the ancient Greeks, etc., all the way through history. That's what's been done. This part in the middle, axioms, proofs, and procedures, got separated out and called mainstream mathematics, or mathematics. That's what we think of as mathematics now. That's not what Aristotle would have thought. I mean, let's take Archimedes. Archimedes wouldn't have thought that as mathematics. Archimedes thought of the whole thing as mathematics, beginning with the real world. But that became carved out as mathematics, mainstream mathematics. And in terms of education, K through 12 education is almost exclusively focused on that. University education in mathematics is focused on those, for very good reasons. That was the gateway. If you couldn't master procedures, you couldn't do any of this stuff. So you had to teach that first. It was the only way. And that's what's changed with the development of technologies that do that for us. But for many thousands of years, this was the only way. That's why I had to spend my entire undergraduate career learning how to be very good at executing many procedures. Today, with all of those technologies, we can use this method in a very different way that's not restricted to those who've passed the exams in calculation. If you're a good thinker and you're logical and you're creative, you can play this game now. You don't have to do the calculations. Which is just as well, because most of the real problems today that require mathematics, they really require a big picture problem approach. As I've mentioned, resources, most of them in the cloud, will do the calculations we need. And for various reasons, I and other people started referring to this whole picture as mathematical thinking. Strictly speaking, this is what mathematicians would say was mathematics anyway. But since mathematics, the word has come to mean that bit in the middle that was in the box, I'm giving in and saying, okay, the word mathematics has been accepted by society to mean something. Let's talk about mathematical thinking when we want to refer to the whole picture. Because that part has faded away. And it's faded away almost exclusively, but not entirely. You sometimes do have to sort of go in and do some of that when you're looking at a problem, applying it to a new domain. We very rarely prove theorems. And if we do, we can probably use machines to help us do it anyway. And that business about the procedures, developing procedures, that's faded away as well. Because that's all been done, starting in '87 with Mathematica and other systems. Because most of the time now, those of us in the business use technology products to do all of that. In other words, it's the stuff that's not faded out, that's what the human beings do, which is good, because human beings are actually very good at doing that. We find it very difficult to do the other stuff, which is why only a few of us were successful at doing it, and why it took us many years of very hard work to learn how to do it. I studied really hard for 3 years to become good at doing something that became obsolete in my lifetime. I don't regret it. It seemed like a cool thing at the time, and it was the only way to get into the game and play the game. The tool I use most of all for that part now is Wolfram Alpha, because it's so simple, easy to use, the interface is great, and it's free. The versions I use are free on the web, but there are many other tools you can use for doing that. Which means that whereas yesterday, if you were a mathematician, you had to be able to play an awful lot of instruments. You had to play the analysis instrument, the calculus instrument, the algebra instrument, the geometry instrument, the trigonometry instrument. We had to play all of those instruments. And you probably had to learn how to play new instruments as well. Today, this is the mathematician. We conduct an orchestra of very skilled players who are almost flawless and very fast learners. There's the orchestra. That's the orchestra we play when we do mathematics. So the whole sensation of solving a problem using mathematics today is very much like controlling an orchestra, conducting an orchestra. To be a good conductor, you probably have to have played some instruments reasonably well, but not perfect. And you should be able to acquire an instrument to get a sense of it, but you don't have to become an expert at it because there's other experts there in the orchestra. And that's the same here. So what does it take to do that? Well, you need a bunch of things. These have already been mentioned already. You need things like number sense. This is not an exhaustive list. I'm just putting 3 that came straight to mind. You need number sense, which is this general fluidity and flexibility with numbers, what they mean. You certainly need that kind of stuff. You certainly need deductive reasoning skills. You need to have creative problem-solving ability, which would include things like algorithmic reasoning, metacognitive skills, and a bunch of other things. But these are things that are not exclusive to mathematicians. These are things that are very widely found in the human world. With the focus being on the thinking. Now, having said that, people will say, oh, are you saying content's not important? No, of course it is. The choice of, in some sense it's not, because you could learn how to do this with any bit of mathematics. But since you can learn it with any bit of mathematics, why not learn it with mathematics that's relevant today and which, because it's relevant, is engaging to the learners, particularly young learners. So use examples, use topics that are relevant, self-evidently relevant, and are very engaging. For example, things like probability, statistical theory, network theory, these are far better than calculus. Calculus was a big deal in the 17th century. It remained a big deal to the end of the 19th century, but then it's essentially faded away except in the high school classrooms. Ultimately, however, what's really important is how the topic is approached. So we have to be wise about the choice of topics for a variety of societal and cognitive reasons for people's engagement, but what's really important is how we teach it. For example, look at geometry. That's the classical image we have of geometry. But geometry is more than that. It's about the shape. It's mathematics of shape. And in today's world, there are many shapes more interesting than red triangles. And the real power of mathematics lies in its capacity to reveal the invisible, to make the invisible visible. Here are 2 examples of Euclidean geometry. That's 2-dimensional Euclidean geometry. That's 4-dimensional Euclidean geometry. The one on the left was very useful in that era. The one on the right is an example created by a Manhattan-based artist called Tony Robbins. That was meant to be a mathematically created visualization to understand the complexities of life in a modern, multicultural, multilinguistic, multiracial society, where in the same three-dimensional space, you have all of these different cultural, linguistic, and social spaces interacting. So this shows you how many spaces can come together in the same two-dimensional space. At which point you may say, and some people do say, yeah, but that's just art. Well, there's two answers to that. One is art is one of the best tools we've got for understanding the complexities of life. And this, when you start looking at it, can help you understand this modern complex life just as much as Picasso's Cubism can help you understand dimension and the human form. But if you want more explanation of why it's useful, let's go all the way from the art gallery to national defense. This is actually a product that I specified out for a project I did for the US Army a few years ago. That thing in yellow is a geometric representation, like Tony Robbins' three-dimensional geometric representation of New York, that represents all of the invisible structures on the modern airborne battlefield. Commands, information networks, communications, threats, plans, capabilities, all of that is captured in this interactive, rather complex, but somewhat simple, simplistic diagram, that little geometric thing. It's based on work that was done at Stanford in the 1990s onwards. It's interactive, and it's all linked in a system to the thing. But I didn't have security clearance, so I have no idea what they did with this after I submitted the report. I worked on this for about a year, then just got out of it. But the idea was to be able to have safe interactions in places like Baghdad, that was Baghdad, that minimize what they call collateral damage. Okay. How do the pros actually work, given all of these tools? Same as happens in computer science with coding. We use heuristics. Wikipedia, my second most favorite resource, tells me that heuristic is a practical method not guaranteed to be optimal or perfect, but sufficient. That's the way it's done. When you have unlimited fast computing power at your disposal, you don't waste time thinking about things mindlessly. You do some thinking, but you can just run lots of examples quickly to get an understanding. And to give you an example, and this is my final point, and then I'll have a conclusion sign. This is the one little quiz. I'm going to give you a simple little math question, the kind that you'll find all over the place, that you will answer quickly. In fact, I want you to answer this instantly. Don't try to be deep. Come up with an answer as quick, because I'm not interested in whether you get it right. What I want to know is, how does your brain work when you're faced with a problem? What does your brain do naturally, given whatever training it's had? What do we do when we meet this problem? A bat and a ball costs $1.10. The bat costs $1 more than the ball. How much does the ball cost on its own? No special pricing deal. You don't have to tell anybody, but at least 50% of the audience did this. And this is a really smart solution. You say to yourself, it says more. It's a subtraction problem. You've instantly categorized it with a heuristic. It's about subtraction. You have two numbers, $1.10 and $1. So what do? You subtract the smaller one from the larger one because you know, as a smart person, the answer is going to be positive. So you subtract the smaller from the bigger one, and you get the answer 10 cents. Which is not correct, but you have been smart. You used a heuristic, it's fast, and the reason you used it is you know it usually works. This is a question that's been worded in a rather nasty way to fool the brain, because you're being very smart as a human. How would a computer do it, or someone who's forced to do it in a 1950s classroom as I was? You'd go through this. Let X be the cost of the bat, Y the cost of the ball, grind. You get the right answer of 5 cents, but it's a procedure. It's slow, but it does always work. And it was fine for thousands of years if you wanted right answers. But nobody would do that because even a simple like that one, you can probably do it anyway. But it's slightly more complicated. You use a calculator. This can be written in technology. Here's the third solution. This is the modern tool that corresponds to that one. And this is actually something that Stanislas Dehaene just mentioned. You sort of go from the symbols to what they mean. You say to yourself, it's about costs. There's a cost of a ball. So you have some sense in your mind. I've written it as a space. There's some size attached to it, some quantity. The cost of the bat is the same, but it's $1 more. So you have these images of the two things. You don't have to calculate now. You can read off from that image what the cost is, because the ball plus the bat together is $1.10. So that plus that plus that is $1.10. That's $1. So those are 5 cents each. We haven't done any calculation. We've used pattern recognition. And boy, are humans good at pattern recognition. We're using the same kind of fast heuristics, but at a more sophisticated level that won't lead us astray. There's terminology for this. That's usually known now as rigorous thinking. That becomes pre-rigorous thinking. And this is what we do today, post-rigorous thinking. That terminology, by the way, is due to Terence Tao, one of the best mathematicians in the world from Adelaide, now in the United States at UCLA. And he has observed that this is how pure mathematicians do pure mathematics today, using heuristics. The pure mathematicians do the same thing. So the question is, and this is the final question, how do we teach for using mathematical heuristics? Well, this is where we don't throw away the baby with the bathwater. Almost certainly, and there's lots written on this, we need to go through rigorous thinking. In fact, we need to do a lot of practice to get to the point where you can use those symbols, because as Dehaene said, the fact that you've got the language for the symbols is what gives you the precision. You may not need to do the execution, but you need that symbolic representation, as far as we know, in order to do this kind of thing. So there's a lot of practice required. But remember, the classical algorithms were optimized for efficient performance, which computers can now do. What that means is when we teach these things, we do teach algorithms, but we use algorithms that are optimized for understanding. Because the one thing the computer doesn't bring to the picture is understanding. And if you're working on a real-world problem, one of you and the computer has to understand it. And it's the human being that's going to have to do that. And with access to computers, through computers, we've got so much access to data. We can actually teach this using real data. I've taught high school classes where we have reversed engineered algorithms used by the major companies. At a high school in San Francisco in January, a group of 15 middle to high school students, in the space of 6 hours, reversed engineered the UPS package routing algorithm, one of the most valuable algorithms in the world. We didn't get all the bells and whistles, but we understood how it worked just by reverse engineering it on publicly available data using fast computing power. Content absolutely matters, but in order to be a user, a conductor of the mathematical orchestra of today, the focus very much has to be on using all of that content to develop the valuable way of thinking. Thank you.